All right, let's talk about hydration. We've already mentioned this before. We said this is the chemical reaction that steel and concrete goes through. The steel and the concrete, concrete hydrates. But it's the cement paste, the Portland cement, and the water that go through hydration. It's a fairly complex chemical reaction. What happens is the water molecule, when it's first mixed, actually comes and hydrates the unhydrated cement grain. So there's a particle of cement, the water is mixed with it and begins a reaction. And that reaction starts on the surface, and it takes some time. It goes through certain stages of things that go on. It's dormant for a fairly long time. I'll say 2 hours. Now that 2 hours is just general, depends on a boatload of other things. But in general, if you were to look at a graph of the rate of hydration, how fast the chemical reaction is actually going, within the first 15 minutes, it goes extremely quickly. Now, the first 15 minutes, what's hydrating is what they call the illuminate portion, which really doesn't do anything to strength. Okay? So there's stuff that's hydrating right away, but it's not making it stiff. It's not making it strong. It is hydrating very quickly. But then, for about 2 hours, nothing, sort of happens. The hydration reaction, the rate at which things are occurring just drops almost down to nothing. But what's happening here is that the mix is starting to be flooded with calcium ions and other ions. The reaction's going onwards at a slow rate, but there's things that are starting to flood into the solution. After about 2 hours, that's when it all changes. All of a sudden then, the hydration reaction kicks up again very quickly. And it peaks out, all these time values I'm giving are just general, but it peaks out in normal times maybe at 8 to 12 hours. Okay? And then at that point in time, it starts drifting on downwards and downwards and downwards and whatever. So, here's what's happening. Here's why you care about that graph. How long do you have to get concrete into its forms, placed and into its forms and all that stuff? Right, roughly it's about here. Whether that's an hour, 90 minutes, 2 hours, whatever. This first hydration, they call it the illuminate portion of hydration, doesn't make it strong, doesn't make it, doesn't harden the concrete. It's hydrating, it's just not doing a whole lot. Okay? You have until about this 1 to 2 hour mark to get the concrete in, because after that point in time, the rate of hydration is going to kick up, and this is where you'll start getting what people refer to as the initial set. The concrete will begin to harden. Okay? It's not hard enough to walk on it yet. It's not hard enough to push a wheelbarrow across it. But you can see it's starting to stiffen up. All right? After about maybe 4 hours, maybe 6 hours, something like that, that's probably what they're going to call the final set. At this point in time, the concrete can support some loads. Not like you're going to drive a truck across it or anything, but you can walk on it. All right? Maybe don't want to walk on it, but there's a point in time where it starts to be able to support loads. Okay, so people talk about initial set, final set, and again, you know, whether you want to say the initial set's 2 hours, 3 hours, whether you want to say the final set's 4 hours, 6 hours, 8 hours, whatever. There's the portion of time where it begins to set up, and then the final set is where they say, now it can start to support regular, you know, lighter loads and stuff. Okay? Hydration reaction continues, like I say, for let's say 12 hours or so, peaks out at 12 hours, and then drops off. It continues on forever. The reason it slows down here is that what's really happening at this point onwards, this is where the concrete starts to harden up. I mean, it begins to, and it continues to harden up after this time. The reason it does it here is all these things that were, for these ions that were flooding into the mix, they begin to form crystals. And that's how concrete gets hard. There's a crystalline matrix. There's several different types of crystals that are created that actually begin to grow and form and actually sort of put their arms around the aggregate and to bind them together. Concrete isn't a glue as we know a glue. Concrete is really a glue that forms a bunch of crystals, and these crystals sort of interlock with each other and interlock around the aggregate and hold on to the aggregate. That's how concrete gets hard. It's really this formation of crystals. Okay? It peaks, you know, the rate of hydration peaks out, you know, 8, 12 hours, whatever, somewhere in there, simply because there's less unhydrated cement available. And also the water that's available is having a tougher time of getting through all these crystals to hydrate cement. So that's why it starts to slow down. But you can have concrete that's 75 years old and hydration's still occurring because there's still that one water molecule out there that all of a sudden found that unhydrated cement grain 75 years later. Hydration still occurs. So there's still this crystalline growth. So that's, you know, what happens. The crystal, there's a couple crystals that form. The crystal that we care about is a crystal called CSH. And that crystal, CSH, stands for calcium silicate hydrate. Out of the matrix of all the crystals, this probably makes up 50% or more. And this is the good stuff. This is the really good stuff. CSH, you can think of, causes stuff to harden. Okay? Because this is, when you talk about strength in concrete, the facilitating the formation of CSH is a good thing. Okay? There's other crystals that form. Another crystal that forms a fair amount is called calcium hydroxide. And that's really not so much strength related, and actually, if we can, that can cause us problems later on. Yeah.
I was just trying to ask you what CSH stand for again.
Calcium silicate hydrate. Calcium silicate hydrate. And you know, we talked about the pozzolanic material. We said how it reacts with something later on to actually help us out. What it reacts with calcium, there's this calcium hydroxide that's formed too. About 50% of the crystals are this, about 25% of the crystals are that, or 30%. This is the really good stuff. This stuff, not so good. All right, and it can cause us problems later on too. What was all the pozzolanic material very high in? Silicates. Some hydration forms this and this. If I put pozzolans in it, those silicates find their way here and create more CSH. That's why those pozzolanic materials are are good. That's why they work. They don't work, they combine with water. They work because they combine with this. So they'll call them a secondary type of cementitious material or supplemental cementitious material. It's because they don't work like cement and water. They zero in on this other stuff, which we're sort of like, this is really not the greatest stuff in the world. All of a sudden we put an S in there, now it's the greatest stuff in the world. Okay? So that's a little bit about hydration.